This is the 7th part of the tutorial about history analysis in RayJack ONE. In this video we will learn how to show ray trajectories in a system viewer after ray tracing. By ray trajectory we mean the piecewise linear curve that describes the propagation of a ray through the 3D optical system. In order to access ray trajectory data after ray tracing, we need to set up the history detector to record the relevant interaction data. To this end, we define history settings record trajectory equals true. Alternatively, we can also set history.settings.record all interaction data equals true. This includes the trajectory data, but also the other data that we might need for path analysis. With these history settings, we can now run the ray tracing simulation. And once the ray tracing is finished, we can study the ray trajectory data. In a previous video, we have already seen how to visualize the ray trajectories for a given path. To this end, we first show the grid view of the paths. With the command history dot grid view. And then we can pick a path, for example, the path with the ID number 14. And then we right-click into this row and click on Show Optical System and Trajectories of Path 14 in a new system view. This opens a system view together with the ray trajectories of the corresponding paths. Now we will see how we can achieve the same result from script. The relevant command is the command history dot show trajectories. And this command accepts a couple of different input arguments. We can either provide a ray collection, or we can provide a path object, or a path ID, a path condition, path collection, or a ray filter. In this case, we want to use the path ID. As we can see, again, the same ray trajectories are shown for the given path. Showing the ray trajectories for a given path is probably the most important application of the history.showTrajectories command. However, we could have provided any ray collection here. Using this command with the path ID argument is just a shortcut to first getting the rays, like this, and then calling history.showTrajectories with these rays as the input argument. It is also possible to combine the ray trajectories of different ray collections in a single system view. To this end, we call the command history.showTrajectories twice. When calling it for the first time, we create a new system viewer object, which we can assign to a Python variable. Let us also define a color in which the ray trajectories should be plotted. In a second step, we again call the command history.showTrajectories with a different path ID for example 24. And this time we use the viewer keyword argument to tell RayJack ONE that the trajectories should not be shown in a new system viewer object, but in an already existing system viewer, which is assigned to the Python variable viewer. And finally, we define a different color such that the ray trajectories can be distinguished from the ones that with the path ID 14. Let us run these commands to see the result. And as we can see, the ray trajectories for two different paths are now shown together in different colors. Let us finally turn to the topic of slow motion videos. This is a nice little feature of RayJack ONE, which allows us to generate animated videos of ray trajectories. The command that we need to generate such a video is history.slowmotion. As an input argument to this command, we can either provide a list of path IDs, a list of path objects, a single ray collection, or a list of ray collections. Let us for the moment assume that we wanted to generate a video showing the trajectories of the rays which belong to the paths with the ID 14, 24, and 34. So we define a list of path IDs and give this list to the command history.slowmotion. Let us check what other input arguments there are. So all of these arguments are optional. For example, we can define a system viewer object, and we can also define a list of colors. The list of colors corresponds to the list of path IDs. For example, we can define that the rays belonging to path number 14 should be colored in red. The rays belonging to path number 24 should be colored in yellow. And finally, the rays belonging to the path ID number 34 should be colored in blue. It also makes sense to define a viewer object beforehand, because this allows us to also set a cut plane. Cut plane should be along axis X at position 0. And we can also define the input argument affect rays and set it to false. And this way the cut plane will only cut the optical system, but will not cut the rays. So we have a viewer, we have a list of colors. Now there is a bunch of parameters of type float which refer to the optical path length. So there's an optical path length start, optical path length end, and optical path length increment. And here optical path length can be understood as the time of the slow motion video. We need to set the optical path length end to a number of 300. No, I think it was 500, because this ensures that also the longer trajectories will be shown until all the rays are propagated to their end. And finally, we also want to define a frame delay and set it to 10. Now let us run all of these commands to see what happens. And we can see a new system view with a cut plane. And RayJack ONE now plots the ray trajectories in that system view for the individual paths. And for each frame, the trajectories are truncated at a certain optical path length. And this truncation optical path length is growing such that we get the impression that the rays are propagating through the optical system in real time. It takes a while to finish this process, and once the last frame has been recorded, RayJack ONE still needs some time to wrap everything up into a single GIF animation. So we need to wait for this to finish. And as soon as we can see the message GIF export completed in the output console, we can check our project folder for a file called trajectory_animation.gif. And opening that file will show us the resulting slow motion video where we can see how the ray trajectories of the individual paths propagate through the optical system. So in this video we have learned how to show ray trajectories in a system viewer and how to generate slow motion videos of ray trajectories.